In this video, we'll continue to look at questions on atomic physics, nuclear physics, radioactivity. Now this time, we're going to be looking at another past paper question. This question is from May, June 2016, and this would be question 1. So May, June 2016, question 1, right? So the question says, the activity of a radioactive sample was measured over a 6-hour period. The results are recorded in table 1. So here I'll already go on ahead and copy down the table, right? So we see the time in hours and the activity A in disintegrations per second. I couldn't bother to write out the word all of disintegrations per second. So activity A in disintegrations per second, right? So we see that time T in hours goes up to 6 hours. So initial activity 80.0 after 1 hour, 50.0. 34.5 after 2, 20.0 after 3, 4, 30.0 after 4, 7.5 after 5, and 5.0 after 6 hours, right? So part A of the question basically wants us to plot a graph. So this is using a grid, which have been given in the booklet on page 5. Plot a graph of activity A versus time T. I've also gone ahead and basically drawn my pair of x and y axes. I have the time in hours on the x-axis and the activity in disintegrations per second on the y-axis, and I've basically chosen a scale. I think I use a scale of 2 inches to represent 1 hour on the x-axis, and of course I use a scale of 2 inches to represent 10 disintegrations per second on the y-axis. So I guess if you were to plot it on the graph paper, you could have used 2 to 1 in terms of 2 centimeters to represent 1 hour and 2 cm to represent 10 disintegrations per second, which is essentially the same thing as 1 cm to represent 5, and so on, right? So I've already drawn the axes, I've plotted the points, and the only thing left for me to do is basically draw my curve of best fit through those points. Now clearly the rest of the board is not ruled, but I'll try to do this as best as I possibly can, right? Right, so there I've tried to draw my curve of best fit, right? So I'll leave it at that, right? It's looking decent enough. Good. So having done that, let's see what else the question asks us to do. So we plot the graph of activity versus time. Of course, when it comes to plotting a graph, we should always make sure that we have all the things that are required for the graph. Our axes are labeled, our scales are stated, and of course a graph of as a title. So I could say graph of activity versus time, right? And of course you go ahead and you state a scale as well. So for the x-axis, I'm using a scale of 2 inches to represent 1 hour. So 2 inches equals 1 hour. And on the y-axis, I'm using a scale of 2 inches to represent 10 disintegrations per second, right? Right, having done that now, so 8 marks to plot in the graph. So clearly you need to more than just draw the axes and put the points, right? So having done that, let's go to part B. Part B says, from your graph, determine the half-life of the sample. Now, in order for you to determine the half-life of the sample from this graph, you would have needed to know exactly what half-life meant. In a previous question, we were asked to define half-life, so that the half-life of any radioactive sample is a time taken for the number of atoms or nuclei or the activity of the sample to decrease to half its value, right? So we can define half-life in terms of number of nuclei or in terms of activity, and it's a time taken for the initial number to fall to half its value. So from the data, we see that at t equals 0, the activity was 80.0. So determine the half-life of this sample. We're going to locate a half of 80, which of course is 40. Then we're going to extend a horizontal line to meet the graph and then drop a vertical to see what time that corresponds to, right? So once again, my board is not ruled in very small grids, so my result might not be as accurate as if you were to actually plot it on graph paper, right? So using the initial activity as 80 disintegrations per second, a half of 80, that is 40. So we locate 40 on the y-axis. And of course, in this question, it is 5 marks. So you basically would need to show how you arrive at the half-life, right? So locating 40 on the y-axis, then drawing a horizontal line across until it meets a curve. And then of course you drop a vertical until it touches the x-axis. Again, this won't be perfect. Right? So based on my scale, it's very close. So this would be 1, 2. This would be approximately 1.5. So let's call it 1.5 hours, right? So from my graph, I could say from my graph, so the activity A equals 80 at t equals 0, and the activity A equals 40 at t equals 1.5 hours. And therefore, the half-life, t half, is equal to 1.5 hours, right? So again, from the graph to determine the half-life, you pick a value. So you could start with the initial activity at t equals 0. You find a half of that value and you locate it on the y-axis. A half of 80, that is 40. You take a ruler, you draw a horizontal line across until it touches the graph or the curve, and then you take a ruler and drop a vertical from that point down to the x-axis. And that value at which that vertical line touches it would be the first estimation of the half-life, right? Now, the question goes on to say, 5 marks for that, by the way, right? Question goes on to say, using a graph, determine a more accurate value of the half-life of the sample. And let me see, how many marks for that? 6 marks for that. So usually what they mean by this is to determine the half-life at least once more and essentially find an average of the half-lives, right? So if you do it twice more and find the average, then you definitely should get your full 6 marks. But in this case, they did not specify how many times you had to do it, so at least once more, and then finding the average would give you a more accurate value of the half-life of the sample. So continuing now, since we already looked at half of 80, which gives us 40, we can now say a half of 40 is 20 and repeat the steps we did before. Oh, by the way, of course, this would be similar to the experiment with the coins and determining the half-life, right? So once again, we locate a half of 40, which is 20. And from our table, did we have 20 in the table? Yes. So from our table, we had 20, which corresponded to 3 hours. So we can just use our ruler to let it reach there. Right. So the second estimation of our half-life, let's just label this. So from 0 to this point here will be the first approximation of our half-life. Let's call that t half 1. And then now, from right here to here, that will be the second approximation of our half-life. Let's call that t half 2, right? So let's call this t half 1 equals 1.5 hours, right? And then now, so say that again from the graph, A equals 20, or we say at A equals 20, right? A is same thing, at A equals 20 when T is equal to 3.0 hours. So therefore, the second approximation, T half 2, will be equal to 3.0 minus 1.5 equals 1.5 hours. So we must remember that for the second half-life is going to be the interval between these 2 points where the broken lines meet, right? So the half-life is not 3, but it is an interval which it takes for the activity to fall to a half of that value. So from 0 or from 80 to 40, that time of course goes from 0 to 1.5 hours. So that time interval of course is 1.5 hours. However, from 40.0 to 20.0, that goes from 1.5 hours to 3 hours, and that interval there, difference between 3 and 1.5, is another 1.5 hours, which of course says that our first approximation was fairly accurate, right? So, and then now we could say that the average half-life is equal to 1.5 plus 1.5 over 2, which gives us 1.5 hours, right? So we need to show that even though the two values are the same, because once again you get 6 marks for this question, and you would have been expected to show that the more accurate value of the half-life is the average of the two half-lives that you would have determined, right? Now in the exam, of course, if you find yourself with a lot of time on your hands, you could go a little bit even further and determine a third approximation of the half-life, right? So if we were to go ahead and do that, a half of 20, that is 10, we then take our ruler and go across until we meet the curve. And well, we don't have the value of 10 on this, so let's see where that takes us. Right, then we take a ruler and drop a vertical from that point down to the x-axis. Right, and that is looking like it is exactly at 4.5. So this interval would be our third approximation of the half-life. Let's call it t half 3. And between 3 and 4.5, we get another half-life of 1.5 hours. So let's just write that down. So we could say now A equals 10 when t is equal to 4.5, and therefore t half 3 would be equal to 4.5 minus 3.0, which gives us another 1.5 hours for the half-life, right? And once again, we simplify the average, or since we recognize that all the three half-lives are 1.5 hours, we could say that, well, you know, the half-life is 1.5, but of course, it is safer to find the average. So in this particular case, we just add a 1.5, divide by 3, and we'll still get 1.5 hours for the half-life of this radioactive sample, right? So that was B part 2 of the question, and 11 marks in total for part B, and 11? What am I checking? No, a line. Maths off. All right, so the first part to plot the graph was 8 marks, right? Then that was part A. Then part B. Part B1 to determine the half-life, that is 5. So 8 plus 5, 13. And then part 2 a further 6. So 19 marks for that first part of the question there, right? Right, so this question is worth 25 marks. All right, so 19 so far. For part C of the question, now it says, from your graph and using dotted lines, determine how long it takes the activity of the sample to be reduced to 10 disintegrations per second from its original activity level. Lovely. So because we actually determined a third half-life and we actually used 10, because we're going from 80 to 40, that's one half-life. 40 to 20, 20 to 10, and we already used broken lines, then if we had actually gone ahead and found the third half-life, then basically all we'd have to do now is to just read off this part of the graph. So it says, from your graph and using dotted lines, determine how long it takes for the activity of the sample to reduce to 10 disintegrations per second from its original activity level. And so from the graph, it would have taken t equals 4.5 hours. Right? So it would have taken t equals 4.5 hours for its initial activity to reduce from 80 to 10. Right? Good. So a further 2 marks there. Then part D of the question says, state one reason why a line drawn through all the points would not form a perfectly smooth curve. Right? So we plotted our points and we basically drew our curve of best fit, which clearly did not pass through all the points. So if we were to actually try to get the line to pass through all the points, we would not get a smooth curve, and this is what this part of the question is asking us to explain or to state one reason why. Now, you have to remember that radioactive decay is a random process, and so basically, even if you were to take consecutive, say, or constant decreases in the activity, those constant decreases will not necessarily take the same time. What does that mean? So for instance, if we're to look at the time intervals which it take for the activity to decrease by 10 disintegrations per second, then it wouldn't mean that we'll get the same amount of time for each decrease of 10. In other words then, right, and so because it is a random decay, we cannot accurately predict how many disintegrations will actually take place in a fixed time interval. Yes, that's another way of saying it. We cannot accurately predict how many disintegrations will take place in a fixed time interval, and as a result of that, when we plot our graph, we will not get a curve of best fit passing through the points due to the random nature of radioactive decay, right? So that would be one reason why a line through all the points would not form a perfectly smooth curve. E. All elements including radioactive substances have an atomic number and mass number. Explain what the two terms mean, right? So let's talk about atomic number. I mean, this is not something that we need to write, so I'll save my marker, right? Because I don't have that many. Right, so when we talk about atomic number for a particular element, the atomic number is essentially the atomic number of any element gives the position of the element in the periodic table, right? However, in terms of say protons and so on, the atomic number basically tells us the number of protons that are within the nucleus of the atom, right? And if it's a regular atom, as it would suggest, then it also tells us the total number of electrons that the atom will have. So for instance, if the atomic number of a particular element is say 20, and if I remember correctly, the 20th element should be calcium. I think so, yeah, 20th element should be calcium, right? It means that it is a 20th element in the periodic table. It has 20 protons inside the nucleus, and overall it has 20 electrons on its shells, right? Similarly, if the atomic number of an element is say 8, which I remember correctly is oxygen, it means it will be the 8th element in the periodic table. It will have 8 protons in its nucleus, and it also have 8 electrons on its shells. So essentially, the atomic number tells the position of the element in the periodic table, and it also tells the number of protons within the nucleus and also the number of electrons within the shells of the atom. Mass number. Essentially, the mass number is the sum of the number of protons and the number of neutrons, right? The mass number is also commonly referred to as the nuclear number. And when we speak about nucleons, we're talking about the particles which are found within the nucleus of the atom. And of course, these are the protons and the neutrons. So typically, the nuclear number is given as the number of protons plus the number of neutrons. And I would have used that equation before of the form A equals Z plus N, right? And typically, that gives us the mass number of the particular element, right? With that in mind, the question might be asked, if the mass number A is found using Z plus N, how is it that not all mass numbers are whole numbers, given that the number of protons and the number of neutrons can wholly be whole numbers? This is due to the fact that, remember that atoms exist as different isotopes, and the mass numbers are usually a combination of the masses of the different isotopes. And for instance, that is why we don't always have a whole number for the mass number. For instance, the mass number of chlorine is taken to be 35.5. Right? And last part of the question, F, says, in medicine, iodine 123. So I'll write that down. So that is written as iodine 123. I'll just write the symbol iodine. Symbol for iodine is a capital I. So I123, and in brackets we have I123. Let me say 1, 2, 3. Right? 1, 2, 3, and 53. So that is given, right? So iodine 123, and it's also written in this form. And as we expressed in previous questions, when you see it in this format, then this represents the mass number, and this represents the atomic or the proton number. And the question asks, what does 1, 2, 3 represent? So 1, 2, 3 represents the mass number or the nuclear number of this particular atom. And that is the end of this question. And again, this question was question 1 from May, June 2016, paper 2. Let me see, 1, 2, 3.